Hi, this is a review of the Cleverscope. This Cleverscope is a USB oscilloscope. It's a two-channel oscilloscope, and I have one. I've had it for a while and been evaluating it. One of the features or actually the main reason that I bought it was it has a unique feature where you can do FRA. FRA is a frequency response analyzer, okay, and it's a power supply designer, which is what I do. I frequently have a need for a frequency response analyzer. At work, I have access to a frequency response analyzer made by Ridley Engineering, which is a very good piece of equipment. However, the cost is around $13,000 for the FRA. And I also have at work access to another piece of equipment, another FRA, and it's even more expensive. It's the the Venable Frequency Response Analyzer. So that one costs around $30,000 at least, a minimum. Both are very good pieces of equipment. However, at the price range, that makes it not affordable to, let's say, a practicing engineer, small company, or maybe even a hobbyist. Okay, so I got or emailed Bart I guess a year ago. I noticed that he had done some Bodie plots, and since he had a function generator that went up to 10 megahertz, and of course the oscilloscope, and he had the capability of doing FFTs, I thought that there was a unique opportunity to change the software to do frequency response analysis. So when I approached him, he was very eager, and he put quite a bit of work. And after giving him some feedback and then some feedback from other power engineers, I think he developed a pretty good piece of equipment, at least from what I can see so far. So the frequency response analyzer, if you go to his Cleverscope.com, he has a video on how to use the gain and phase. And on this video that he did, he has, I guess, the first version of the software. It has changed quite a bit, and I might say that he has improved the sensitivity. One of the major changes that he did was on the recommendation by engineer Bob Rourke. He had suggested that he make the function generator isolated. That way, by making it isolated, he did not have, or we did not have a need to use a transformer as a injector. Basically, on the Ridley and on the Venable, you have to use a transformer to couple the signal into your power supply. With this unit, you don't need an injection transformer. You can connect function generator straight to your Venable point, and then connect your test points and take measurements. So that's very powerful. Another advantage is that with it being direct, you can achieve lower frequency response. With this, you theoretically should be able to go down to 1 hertz. Okay. Now, some of the work that he did a white paper, and on a side note, I provided these plots to him as a comparison to see how well the plots would match. And on this white paper, we try to simulate or use the same conditions to see how close the measurements were. Now, I had noticed that at the first time that he did come up or did the first revision, the high frequency matched very well, but did notice that the low frequency around 10 hertz, they didn't match as well. Okay, and you can see some of it in some of the other plots. For example, here is some of the plots that did not match as well. Okay, this is the measurement that he took, and if you notice, let me see if I can zoom out. Okay, and if you notice right here, although the scaling may be a little bit different, okay, it's a little bit different, it doesn't match as well. Okay, so what I'm going to do is I'm going to attempt to verify, see how well they match now that the software has been written and made more sensitive. I'm going to see how well it matches, and I'm going to try and compare them with these plots. I'm going to try and compare this plot, and here's another plot. If you notice, this is the Venable. Now this is a $30,000 piece of equipment, and if you notice, it has breakpoint at this frequency. Can't read it very well, but I believe it's close to 100 hertz, and it breaks down. But when you look at the first plots that he did on the Cleverscope, we didn't have that breakpoint. So as far as low frequency, it didn't work as well. So I'm going to go ahead and attempt to take this measurement, see how well things match. And what I'm doing is, when I took this measurement, I used an injection transformer because this was taken on a Venable. So in the interest of trying to compare apples to apples, I am using the same injection transformer, and I'm going to try to reproduce this. Now, if you notice up here, it says input voltage 8 volts, output voltage is 5 volts, that's the regular output, and the current was set to 1 amp. So I'm going to go ahead and set the electronic load is already at 1 amp, and I'll lower the voltage to 8 volts, which I am doing now. Okay, so I have my power supply on, the electronic load. So now I'll go ahead and turn the Cleverscope. It's loading. Okay, so this is the Cleverscope, and I've happened to already saved a script with my settings, and I have it as a FRA.APC, call it up, and this is what you get. This icon or menu I don't use, typically hide it, and what I use is this menu, which is the Frequency Response Analyzer. Okay, and sometimes I do use this. However, in this particular case, I'm not going to use. I'll go ahead and minimize it. And another menu that I do use quite a bit is the scope. Okay, now one of the things that I do need to mention, that it's, as far as taking measurements, it's not fully automated. It's semi-automated. When I say automated, when I think of a system that is automated, you set the control panels and you press a button. In this case, it would be the start, and you let it go, and the instrument self-adjusts to give you an output. In this case, it does do that, but it's a little bit limited, and sometimes you might have to do some manual setting to get the optimal results. Okay, so as I run, you'll see where you have to do some of the settings. Okay, so in this case, I'm going to go ahead and try and duplicate this waveform, and I can see that it's from 10 to 100 kilohertz. Okay. So I go to the start frequency, I set it to 10. Okay. The stop frequency, I'm going to go up to 100 kilohertz. And this is the signal generator amplitude. This is the amplitude that the function generator would output. Okay. And then this is an offset voltage. And then this is the steps per decade. And under the sweep action, you can select repeat. In other words, it'll do a sweep from 10 to 100 kilohertz and redo it. And that's a very nice function in case you're actually tweaking or setting your control loop. You can have little pots, you can vary it, and you can adjust on basically on a real-time basis. Or you can do it once. Basically, you press start and then run, and you take your data. Okay, so I'm going to go ahead and set it once. Okay. Now another feature that it has, it's got the constant. Now when they say constant, it means that the signal from the output generator is constant. In other words, if you set it for 6 volts peak to peak, it's going to output 6 volts regardless. In the auto, it uses a control servo. Basically, it looks at channel B, and I believe it adjusts the output to maintain or try to maintain a voltage of 1.1 millivolts. Okay, and it works a little bit slower because it's doing that control, and there's times that you might want to use that function. But I prefer the table, and I believe the table is probably the best option. And the reason is power supplies, especially at low frequencies, they have quite a bit of gain. And when you inject the signal, because you have a lot of gain, when it returns back, the signal is actually attenuated in one of the channels. So typically, on a well-designed power supply, you want the gain at low frequency to be quite high, and then it rolls off, and as you go up higher and higher, you don't require as much signals from the function generator. You actually attenuate it. As a matter of fact, if you go too high, it starts to saturate the op-amps or the ever control op-amp. So in this case, if by looking at the amplitude table, I have a start frequency of 10 hertz, and I'm setting it to a fairly high peak to peak voltage, which is 4, and then at the end I have 100 kilohertz, and I want it to go down to about 1 millivolt of signal. Okay, and then instead of being linear, I would like for it to be in a log fill, and by pressing this you can input just the start and the stop, and it fills these two columns by itself. Okay, so that's basically the setup. Okay, and then these other options, typically you would press amplitude, power, you leave it on, log, interpolate, narrowband, and in some cases we'll go ahead and start with the auto setup in the on position. Now in the auto setup, what it does is supposed to adjust the voltage scale, or the vertical scale, to I guess to the proper level where it can have enough signal to do a proper FET. However, I noticed that sometimes the algorithm is not as doesn't run as well, and sometimes you may have to adjust the vertical to get a good enough signal. And typically you can see if your signal is good enough or not by looking at this, which is the signal to noise ratio. If you have a signal to noise ratio of greater, I believe, than 1.5, then you have good signals. Anything below, then you're in the noise level, and your signal's going to be not as good. Okay, so once I have that, go ahead, it's already set up. I'll press start, and when you press start, you look at this, you can see the signal. Make sure that it's not being saturated. Okay, now one thing that I do notice right now, it's a little low. Okay, but I'm going to go ahead and just leave it like that, just to see what kind of a reading I get, and then I can go ahead and rerun it. And I'm looking at the signal to noise. See a little bit of noise here, and you can tell by looking up there, and then the noise, the signal goes up, and then it comes down. Okay, so you notice we have a pretty good plot here, and then in this here we got a little bit of noise. And typically this is the type of plot that you would get on any of the frequency response analyzers. You'll get it in the Venable, you also get it on the Ridley. If you don't have enough signal inputted into them, you'll get this type. In other words, the signal starts going up and down. And if you notice, I have a little bit of signal in here. Okay, so now this is with the auto. Let me go ahead and rerun it again, and since it's noise, you'll probably get random noise, so the plot will be a little bit different, but I'll show you how you can set it to give you a much more consistent. Again, we're looking at the phase. The signal should be good. Still good. Still good. So far. Some noise there. Okay. Again, it doesn't look as good as I would like it. Okay. So now the way to work around this is to go ahead and turn off. Okay. And I'll go ahead and set it in the repeat mode. Okay. That way I don't have to restart it again. And what I'll do is I'll start increasing this signal. So I can go ahead and increase this, and I increase it until I can see a little bit of a waveform. Okay. And if you notice, the signal to noise ratio numbers are much better. Okay. So once it gets to the end, it's going to rerun. Now if you notice, I've got a little bit of noise here. Okay, there's another way of fixing that. Okay. Running it. It's running. Okay. Now if you notice right here, it's a little noisy. Okay. And that means that I do not have enough signal at the higher frequency. Okay. So that's the power that I have, and that I can vary the amplitude. So right here I need a little bit more signal. So let me go ahead and bump it up to 5 milli. Here's 5. Okay, and that's at 2 kilohertz. So let's see if it fixes that part. Okay, see, now I'm beginning to fix it. Let me go up to 10. Fill. So to 140. It's updating the waveform. Okay. I could probably bump it up a little bit more. But for all intents and purpose, and we could probably even bump this up a little bit with a little signal. Okay, so that looks good. So I'll go ahead and stop it here. Okay, and let me go ahead and compare this. This, I believe, this was a 60 to 180 plot. Let me go ahead and change this. 60 to negative 60. 180. Okay, so now hopefully I can get both of these. If you look, the waveform is almost a match. In other words, prior to the upgrades, the low frequency response was not as accurate. Okay, the gain in the phase was a little lower than expected. And this is what I should have expected. And it's a little bigger. Yeah. If you notice, that is basically a match. Right here, if you look at the venable, you notice that the phase is going up and down. Here, that's a little bit of noise. But for all intents and purpose, this is a pretty good match. So this is a very good indication that the low frequency response, due to the isolated function generator, and also the software modification that has been done to the FRA is working much better. Okay, so let's see if I can try another condition. Okay, this one's a little different. Okay, here's another one that I noticed that was quite different. These are supposed to be the same measurement. Okay, if you notice, the high frequency seems to match, or at least it's similar, but the low frequency is similar to what we're getting. And in this case, the test condition is 24 volts. So I'll go to 24 volts input voltage. Okay, and 1 amp. Okay, 5. So I'm going to see if I get that. Okay. And it's basically almost the same reading, except there's a little hump where it goes up. Just curious to see whether it will reproduce that. Actually, this one has that. But let's go ahead and try that. And what I can do is I'll leave this just to compare. And the way to do that, you press add reference, and what I'll do is I'll keep this waveform. Okay, so remember this is at 12 volts input, 1 amp, so the next one will be with an input voltage of 24 volts, 1 amp as well. So I'll go ahead and press, instead of repeat, I'll press once. Okay. And look at the signal to noise ratio, and I can also look at the scope, make sure that everything's working fine, that it's not being clipped. Okay. So now this is a pretty good feature because now you can compare several different test conditions. Okay. Here's the measurement. Go ahead and do that. Now if you want, you can go ahead and measure the crossover, and you press the FRO, and what this does, it gives you the crossover, it gives you the phase margin, and also gives you the gain margin, and those measurements are captured here. It has the crossover at 10.7 kilohertz with 69 degrees phase, and it's a gain margin of negative 17 dB. Okay. So now you can click between the first plot and the second plot. Okay. So this is the first plot, and let me see if I can hide. Yes. Okay. So now let's see if I can compare it again, and let me set the same scale. Looks like this. So compare it. Okay. So now I can take a look at this, and if you notice, it looks very similar. It crosses over at that's 100. That's 1 kilohertz, a little bit past kilohertz, 1 kilohertz, and that's where they crisscross. Okay, and the unity gain, or the crossover frequency, is just about 10K, and if I look here, it's just below 1K. It's like 9 point something. So they're pretty good. And if the phase looks also very close indeed. So this tells me that I'm getting very good results, and I'm quite pleased with it. Now, it does take a little bit of practice and setting it up, but once it's set up, it works very well. And you do have the tools. In other words, you can look at the signal to noise ratio, and you can adjust the scope vertical amplitude to give you a very good and accurate measurement. Now I'll go ahead and probably do another video with some more detailed ways of using the frequency response. I'll show how to measure the output filter of the power supply. And when I say measure the Bode response. I'll also show how to measure the error amp that has a certain response, especially on a type 2 that we strive to keep. And I'll show how, if you have the response of the output filter and your error amp, you can set your crossover at the desired point that you want. If you have any questions, email me at rbola35618.com, and I'll try to get back and answer your questions. Thank you for watching.